So this is going to be the next part of the video on chapter 13. We're going to call this chapter 13 part 4A because this is actually a really long set of slides, and so I've decided I'm going to not do all of them. I'm going to just call this part A. Okay, so we're going to call this part A. Okay, and then we'll have part B, which will be the last video in chapter 13. All right, so in the last couple of videos, we talked about the integrated rate laws and rate laws in general, and we said that the rate of the reaction, or how fast the reaction goes, depends on the change, actually the change in the concentration over the change in time. And that K is a rate constant, okay? So what we really didn't emphasize, and we're going to emphasize more in this chapter on, is that the fact that the rate actually is also affected by the temperature, not only the concentration, but the temperature. And so the rate constant does vary with temperature, and therefore the rate itself varies with temperature. This can be explained by something called collision theory, and collision theory assumes that for a reaction to occur, the reactant molecules must, 1, collide with an energy greater than some minimum value with the proper orientation, and the minimum energy of collision required for the two molecules is called the energy of activation. Okay, so let's look at what these three things, or these three tenets, are talking about. Okay, so we're going to look at something called the transition state theory. Let me just get out of this here. We're going to look at something called transition state theory, and it basically explains the reaction resulting from the collision of two molecules. Okay, so let's say you have a molecule here. This is called NO, okay, or ON, okay, and this is Cl2, okay. And so let's say that this molecule collides in such a fashion where the blue ball and the green ball collide together. Okay, so basically what happens is this collides with this, okay, and it collides hard enough, with enough energy, with enough kinetic energy, that it actually kicks off this Cl, okay, and you break this Cl-Cl bond, okay. The result is that this new bond is formed here, okay, notice there's a new bond here, and the bond between the Cl and Cl has been broken, okay. So in this situation, what must happen is that momentarily, for a short, very brief period of time, a bond is forming between your nitrogen and your Cl. Okay, so there is a bond forming. Okay, at the same time, instantaneously, there is a bond that is breaking between the Cl and the Cl. This complex, where all four molecules are kind of joined together, is called the activated complex. Okay, the dashed lines show the making and the breaking of the bonds. Okay, this activated complex is very unstable, and it's a grouping of atoms, but it is unstable. Okay, and the result is it will break up and form two separate, distinct products. Okay, so this is what we call the activated complex. Okay, this is also another thing what we often refer to as the transition state. Okay, transition means it's changing from one thing to the other, and so it is the state where this change is happening, right, where the bond is forming and the bond is breaking. Okay, that's why this is called transition state theory. Okay. Now, when we're looking at this, we're going to plot this reactants, products, and the transition state on a potential energy diagram, wherein on the y-axis, we have the energy per mole. On the x-axis, we have the progress of the reaction. And as you know, when things progress, you have a start where the reactants are, okay, and you progress until you get to the end of the reaction, and the end is where the products are, okay. And in the middle, you have something called the transition state, or the activated complex. Okay, if the energy here, let's say this is 0 kilojoules per mole, okay, Your products could be at, let's say, 100. This is your products, right? So not 100, 83. So 83 kilojoules per mole. Okay. Your activated complex is going to be much higher in energy. It's going to be at 85 kilojoules per mole. Okay. And so basically what it's illustrating here is that the potential energy requires, or there is a requirement of energy for this activated complex to be formed. Okay. And what is this required energy? It is the energy of activation, and it is, I don't like how the book has drawn a double-headed arrow. It should be a single-headed arrow pointing upwards. Okay, don't draw a double-headed arrow. Just draw a single-headed arrow pointing upwards from the reactant to the transition state. Okay, the energy of activation is from the reactants to the transition state of the activated complex. Okay, so why is this arrow always positive and pointing up? Okay, it's because forming bond and breaking bond, the result of this is that it requires a certain amount of energy. Okay, the reason for this is, as you can imagine, when you have molecules coming together, okay, around each molecule is the electron cloud, right? We know that outside of the atoms are these electrons. Okay, for the two molecules to come together and form a bond, we're going to have to overlap electrons, right? Because really we know a chemical bond is the sharing of electrons. Okay, and since electrons are negative, they actually repel one another, and so we have to overcome this repelling for a bond to be formed. And so this means that for a new bond to form, it's going to require some amount of energy. Okay, and only if the reactant molecules, when they collide together, have sufficient kinetic energy, is it possible for the potential energy to increase to the value of the activated complex. In this graph here, the activated complex energy requirement is 85 kilojoules. This is what we call a potential energy diagram. Potential energy diagram. Okay, and we're going to learn how to draw these things. Okay, so let's look at an example. Okay, so we're always going to start with two axes, your y-axis and your x-axis, your y-axis and your x-axis. And instead of calling them y and x, we know that the y-axis is actually energy. Energy is always in kilojoules or joules per mole. Okay, and the x-axis is always the reaction progress. And so we always draw a line here for the reactants because we always start the progress here, right? This is always the start. Okay, and so we can draw the products either up high or down low. How do we decide? It is because we need to look at the delta H. If the delta H is negative, okay, then the products should be down here. Okay, and if the reaction is okay, well let's just go with it should be down there. Okay, the reason is this: if you have a number line, okay, and this is always your 0, right? If you're drawing 1, 2, 3, 4, you're going to have to go up, right? 1, 2, 3. If you're going down, it's -1, -2, -3. So as you're going from the reactants to the products is here, the reactant is here, okay? This difference is your delta H, and because you're going from reactants to products and the arrow is pointing down, you're getting more negative, exothermic. Exo is negative, okay? So really what you should draw is, and this is your transition state here, you're going to go up, then go down to the products. Okay. Then, if you want to, let's call this the forward reaction. Okay. For the reverse reaction, we're just going to say, let's go backwards. Let's go from the products to the reactants. So here, we're going to just draw a quick line this way. So this is where we're going to start now. And the reactants is here. So we're going to end here. Okay? Notice in this case, again, we're going to have the same transition state. Okay? We're going to start, go up to the transition state, and go down. Okay? Notice here, the delta H is no longer negative. You start here, then you go up to the products, right? Your delta H is positive. Okay? This is what we call the reverse reaction. Okay? And again, this is your transition state where your activated complex is. Okay? Now, how do you draw the energy of activation? The energy of activation is always from the starting material. Remember what we said, from the reactant to the transition state. So we're going to say from the reactant, I'm going to draw an upward arrow to the transition state. I'm going to do it again. From the reactant, upward to the transition state. Should be a straight vertical line. Okay? Hopefully you kind of understand. From this slide, you need to learn how to draw the reactant, the product. You need to be able to label the delta H, and you need to label the transition state, and you need to know how to label the energy of activation. These are your key things. Okay? Let's do some practice problems so we kind of have a good feel for what's going on here. Okay? It says label on the graph where delta H of the forward reaction is. Okay? So again, I'm going to remind you delta H is always from the reactant to the product. Okay? Always just draw a line. This is the reactant. This is the product. Okay, right? This is the reactant. This is the product. Okay? So from the reactant to the product. From the reactant to the product. Okay? In this case, it's going to be downward, so it is negative 91.8 kilojoules. Okay? And because it is pointing down, it is exothermic, and it is negative. Okay? If the energy of activation is 5 kilojoules, let's label it on the graph. So remember, the energy of activation, or the E of A, is always from the reactant to the transition state, the top of the hill. So that's here. The transition state is here, right? So we're going from the reactant to the transition state. Okay? You can draw it here. A lot of books draw it here. If you don't like to draw it here because there's not enough space, you can always draw it here. That's okay too. Okay? But really, this is the energy of the activation. It is plus 5 kilojoules per mole in this case. Okay? And what is the energy of activation for the reverse? Well, let's draw the reverse, right? The reverse is going to be the NH2 is, sorry, and the NH3 is down here, right? And my N2, 3H2 is up here. And I've got my transition state up here. So my reverse reaction is going to look like this. Okay? So the energy of activation is, again, from the reactant to the transition state. So that's from here to here. Okay? In this case, it would be 91.8 plus 5, or 96.8, right? Kilojoules. Okay? If they had asked you what is the delta H, again, you would start with the reactants and go all the way up to the products. The products is here, right? Oops, here, right? So it's going to be from here to here. In this case, the delta H would be positive 91.8. Okay? This is the forward reaction. This is the reverse reaction. Okay? In terms of this, we'll give you one more practice problem. Let's label on the graph where is the delta H of the forward reaction. And again, the forward reaction is always going to be, delta H is always going to be from the reactant to the product. Okay, so I'm just going to draw a line this way. Okay, and the book has actually drawn a line here to the products and to the transition state. So let's label everything. This is the transition state. This is the reactant. This is the product. Okay, so why don't you pause the video and see if you can do this problem yourself, and then we'll go ahead and do it together. Okay, so hopefully you've gone ahead and practiced this problem. So the delta H going from the reactant to the product is going to be from here to here. Reactant to product. This is your delta H. Okay, you could have also drawn it from here to here. It makes no difference, just as long as you start out at the reactant line and end at the product line. Okay, so I would say this is what, 45 minus 20. So delta H is going to be 45 minus 20, or 15. Sorry, 25, just kidding. 25 kilojoules per mole. Okay, and is it positive or negative? Since the arrow is pointing up, it should be positive. Okay, is it exo or endo? Since it's positive, it should be endo. Is the energy? What is the energy of activation for the forward product? And again, remember the energy of activation is E of A. It is always from the reactant to the transition state. So again, we're going from the reactant to the transition state. That's this. Okay, so that's going to be, sorry, E of A is going to be, let's see, 50 minus 20, or 30 kilojoules per mole. Okay, so we're going from 50 and we're going to subtract the 20. Okay, and it's positive because the arrow is always pointing up. And what is the E of A for the reverse? Now at this point, again, you should draw your reverse reaction. And your reverse reaction, you're going to start with 50. Sorry, start with 45. Sorry, 45. Okay. Okay, because this is at 45. Okay, and then you're going to end at 20. Okay, and you're just going to draw up and down. Okay, and so this transition state hits at 50, just like up here. Okay, so very quickly, what is the energy of activation? It's going to be from the starting material to the transition state. So it is going to be 5. Okay, if they had asked you what is the delta H would again be from the starting material to the product. So from the starting to the product. So really it would be 45 minus 20. Again, it would be down because it is negative. So it would be minus 25 kilojoules per mole. Okay, hopefully this gives you a good idea of how to do potential energy diagrams. I would stop the video here and do the problem on potential energy diagrams. I believe there are 2 of them in your homework booklet. All right, I'm going to stop the video here and finish part this last video. There's one more video for this chapter on chapter 13. All right, so I'm going to stop the video here.